Okay, so how do we actually make the phylogenies that we've been looking at? So making accurate trees requires three things. First of all, we want characters that change rarely, and we want this because we want a low chance of homoplasy due to reversals. If you're using characters that are changing back and forth all the time, your evolutionary history will have lots of reversals in it. That'll contribute lots of homoplasy, and it will be difficult for you to get the correct phylogeny. We also want to have some knowledge of the characters and the organisms themselves, and that's to help us identify cases of homoplasy due to convergence. We know that certain organisms are adapting to similar conditions. We can maybe predict convergence and beware of homoplasy that may arise from that. Now, in truth, one of the reasons we use molecular data is because we have so many characters that even if this is happening, all that is overwhelmed by the majority of good data, right? Having 90 correct and 10 that are exhibiting homoplasy, you're still going to get a better tree than if you were using a smaller amount of data where maybe you had 9 correct and 1 that was incorrect. That would give you more noise. And then the third thing we need is we need a knowledge of tree reconstruction and comparison methods and tools. So that there are a variety of different methods that people use to make trees, and there are different ways to compare trees once we have made them. So getting the right tree, there's two steps. First, tree reconstruction. We're going to use some sort of algorithm or procedure to make a tree. And then turns out there's no guarantee that we'll get the right tree, so we'll often have several trees that we compare, and then we need a way of doing tree comparisons. So using a criterion to decide between alternate trees. We generally do both of these things when we're trying to get our phylogeny. So tree reconstruction is talk about two techniques. There are others. The first technique you can imagine would be exhaustive search, right? So you could take your taxa, you could make all the different trees you could possibly make, and then use your tree comparison criteria and pick the best one. That runs into some trouble, as we see. So this is the only tree that exists for taxa A and B. If we have 3 taxa, these are the 3 possible trees, with either A, B, or C as the outgroup, and B and C is sister taxa, A and B is sister taxa, A and C is sister taxa. When we have 4 different taxa, this is how many trees are possible. And you can see the number is going up quickly, and in fact it's going up even faster than exponential. So you don't have to memorize this equation. This is just there so you can see what's going on. But if we plot the number of taxa versus the number of trees, you can see that kind of by the time you get to 10 taxa, you're at 34 million possible trees. And by the time you get to 20 taxa, which is not that many different species, you're practically to a mole of different trees that you would be having to compare to each other using your criteria. And so in practical purposes, that means this exhaustive search technique is not feasible even with fast computers for more than about 11 or 12 taxa. So since it's not feasible for anything really interesting, we need a different approach. So a different approach to tree reconstruction would be to use an algorithm to make a tree. So there are lots of different algorithms. Here's kind of the simplest conceptual one. First of all, we compute the distances between all the taxa, right? So take all the taxa, compare them all to each other, calculate distances between all the pairs, take the 2 that are the closest, connect them to each other, group them together, and give them a new name, call them some sort of new taxa. And then recompute distances between the reduced set of taxa, right? You get 1 less now. You're going to calculate all those distances again, and you have this new taxa you have to recalculate distances for. And then you pick the 2 that are now the closest, reduce them, repeat, and that will get you a tree. Again, that's not guaranteed to get you the best tree. It will probably get you a reasonable tree, but it is not guaranteed to get you the best tree. So then what we end up doing is we start with a good tree, probably one that comes from something like this. And what you can do is swap branches randomly. You can basically kind of cut and paste pieces of the tree and move them to other parts of the tree, right? So take monophyletic groups, cut them, and stick them in other parts of the tree. And then when you do this, do a cut and paste, you calculate whether your tree is better than your previous tree by whatever criteria you're using. If it's better, keep the new tree. If it's not better, undo your cut and paste, go back to your previous tree, and do a different cut and paste, and see if you get a better tree. So in reality, when we're doing tree reconstruction, we use an algorithm to get a starter tree, and then we do a long series of these kind of trying to find a better tree, and we try for a while, and after a while, if we can't find a better one, then we are happy with the one we did find. So what are the ways in which we compare trees? So tree comparison criteria. The first one, kind of the simplest idea, is something called parsimony. So parsimony is the idea that the tree that has the fewest evolutionary events is the most likely one. So if you're comparing different trees, the tree that requires the fewest synapomorphies, for example, or the fewest transitions, is the most likely one. Parsimony assumes that evolutionary events are rare, therefore when we try to reconstruct the past, the reconstruction has the fewest events is most likely to be accurate. So this is like a version of Occam's razor. So Occam's razor is this philosophical idea that if you have two explanations for something, the simplest one is probably right. Of course, it's not a guarantee that it would be right, but usually the simplest explanations are correct, and the really complicated, convoluted, fancy explanations, although they're sometimes true, they're less often true. So if we don't really know what's true, we tend to prefer to go with the simpler one, and so parsimony works on that sort of logic, right? The most likely sort of evolutionary history is the simplest one that has the least amount of evolutionary event happening. So here's an example of using parsimony. So I've shown three trees here, and actually the two on the right here are identical phylogenetic trees. This is different. And say we already knew outgroup information, or maybe if we're thinking about E as the outgroup, we knew that the ancestor started off as red, red, red. Now for all of these, the taxa are the same. A and B are red, C and D are green, E is red. That set of current traits are the same in all three of these examples. If this is the evolutionary history, if we're looking at this tree, starting from red, this pattern in modern taxa can occur just by one evolutionary event, right? Somewhere in this lineage, this common ancestor of C and D evolves from red into green, and then the descendants inherit green. And that's how you get C and D being green, while A, B, and E are staying red. This phylogeny would allow you to only require one evolutionary event to get this pattern. On the other hand, if we're looking at this phylogeny, this pattern of branches here, if you start off red, to get C and D to be green, there's two options. Either this ancestor of C and D here can change from red to green, then D will inherit green, C will inherit green, but then you have to have a reversal, right? This individual lineage here has to go from green back into red so that A and B will be red. Alternately, with the same phylogeny, you could have this organism here remain red, but there'd be a change from red to green here, a second change from red to green there, and then they would just inherit this red that was the ancestral state. So here we would require convergence, but we still require two evolutionary events. So to get this modern pattern in the taxa, with this tree, you require 1, 2 changes, a reversal. In this tree, you require 1, 2 changes, right, a convergence. Whereas in this tree, only one evolutionary event is required. Therefore, if we're trying to decide, do we prefer this tree or do we prefer this tree, we'll go with this tree because it is more parsimonious. It only requires one change. It requires fewer than the others. And so when we're comparing different trees, we can look and see what is the minimum number of evolutionary events needed on each of our trees to get the current taxa, and we'll prefer the one with whatever the minimum is, and we'll kind of discard or not like as much the phylogenies that would require more evolutionary events. That's the simple approach. There are more complicated approaches, term them model-based approaches. These are computer intensive. This is a case in which you assume a specific model of evolution, and this could be a very complicated model for the probability of evolutionary events occurring, and you compare trees using these models. So for example, if you think about on our previous slide, maybe for some reason we think changing from green to red is much easier than changing from red to green. Well, if that's the case, then we don't just want to count the number of changes, we would want to count some of them differently, right? Weight some of them more than others. And with DNA data, we can certainly do this, right? So certain nucleotides mutate into other nucleotides much more often. So we would expect to see more of those sorts of changes and fewer of the sorts of changes that are less likely due to the way mutations work. So we might want to count a certain type of mutation as being 2 or 3 times less likely than another. If we start making a model like that, where we're getting more complicated and we're not just counting changes, we're thinking about how likely certain changes are, obviously that's a lot more complicated, so we're going to use computers. It's more than just parsimony, because it's also including statements about how likely we think certain types of evolutionary events are. In reality, we do use model-based approaches a lot more than parsimony, because we do now actually have good data that certain types of evolutionary nucleotide changes are more likely than others. Certain types of amino acid changes are more likely than others. Certain parts of the genome evolve faster than other parts of the genome. And since we know those things and we have that data, we can incorporate it into these models to allow us to get better, more accurate phylogenies than if we were to use parsimony itself, which is a very simplistic approach. Now, when we're doing these model-based approaches, at the end of the day, we're going to use either something called maximum likelihood, which is computing the probability of seeing the data we observe given a tree. Right? So we have our tree. From that tree, we calculate what's the probability that it would give us the data that we get. Then we take all our trees, do this calculation, and we're going to pick the tree with the highest probability. So we're doing the probability of data given the tree, have a bunch of trees, calculate all these probabilities, and pick the one with the highest probability. That's a technique called maximum likelihood. The opposite of this, or kind of a related idea, but going kind of the other way, is using Bayesian techniques. For Bayesian techniques, we compute the probability of getting the tree we're assuming given the data we have. We do this for a bunch of different types of data. We look at all the different trees, and we pick the tree that has the highest probability. So the probability of getting that tree from that data, calculate those probabilities, pick the one with the highest probability. This is a little bit less intuitive, a little harder to understand, and was harder to figure out the mathematics of. So these techniques came later in kind of the history of doing phylogenetics. This was the technique that was used first after parsimony. Turns out that this technique, once you've kind of done all the hard thinking and computer coding, this technique is actually much faster, so it can be done with much larger sets of taxa. So if we think about the history of people who make phylogenies, well, first we made phylogenies just based on how we thought things probably were related. Then we used a system, we used parsimony. Then we started using maximum likelihood approaches, and now we tend to use Bayesian approaches, and in reality what people tend to do is both Bayesian and maximum likelihood and report the results of both of those. So parsimony is the sort of technique that we can easily understand and can have like on exams and assignments and things like that. But we should be aware that maximum likelihood and Bayesian is what professionals use when they're actually making these phylogenies. But you can also see it's based on the same sort of idea. It's still based on picking a tree that has the least amount of unusual evolutionary events occurring. It's just with these maximum likelihood and Bayesian techniques, we don't just count the number of changes, we use more sophisticated data. But once we have a tree, how sure are we really, right? So if you go back and think about what you learned in biostats, you can calculate the mean and the difference between two groups, group A, group B, the means are different. How sure are you that that's a genuine, significant difference? Well, we calculated p-values back then, right? Well, we don't really have p-values for our trees yet. But if you think about statistics, you want to recall that statistics uses the probability that we would get the results we do if only randomness was going on, right? So what p-values are is the probability we get certain results if only randomness is happening. When that probability is low, then we decide that non-random things are happening, right? This is the basic philosophy of how statistics works, right? So testing an observed pattern against randomness is the central idea in statistics. All those different statistical tests you learned did this. So if we're to try to do some statistics with our phylogenies, we want to see how randomness, or stochasticity, influences the patterns we see. How does randomness change our phylogenies? So the standard statistical technique to determine the validity of a tree involves resampling our data to see how robust or repeatable the tree is. In other words, do we get the same tree every single time when we resample our data? When we go back to our data and look at it in a different way, like a slightly different version of our data, do we keep getting the same tree over and over again? If we do, then we're confident that that's probably the right tree. On the other hand, if every time we have a slightly different set of data, we get a different tree, then we're not going to have a lot of confidence in any particular tree that we come up with. So this resampling of data, there's two types of resampling that are done. The first is called bootstrapping. Bootstrapping is resampling with replacement to create a new data set. What you do is you go to your data set and you pick out n characters, and you might pick the same one more than once, and then you would not pick some of the other ones, right? You're going back to your data and randomly picking values to make a new data set. And so this conceptually simulates robustness to gathering even more data. It has this name of bootstrapping because it's kind of like it's getting more data from not more information. There's this old story about a guy called Baron von Munchausen who was stuck in the mud and he couldn't get out, and he reached out, he grabbed the straps on his boots, he lifted up, and it like lifted him out of the mud, which is kind of an unrealistic thing, right? He's creating an upward force in an unrealistic manner. The name comes from that kind of metaphor. We're creating new data from the data we already have by randomly picking subsets of it. But we're able to simulate robustness because when you pick these subsets, you're kind of testing, what if I have data that looks really similar but is different because some values are missing and some values are duplicated? And if you keep getting the same tree every time you bootstrap, you're going to be confident that that's probably the right tree. There's a related technique called jackknifing, which is subsampling without replacement to create a smaller data set. So maybe just look at the first half of your data and make a tree from that. Maybe look at the second half of your data, make a tree from that, and see if you get the same tree and with both data sets. So you're picking n characters in the set, and you're not duplicating some, and you're going to skip some. And this kind of conceptually simulates the robustness to having gathered less data. So if you had less data, would you also get the same tree? This used to be done because doing this sort of stuff is computationally expensive with computers. The truth is that this is really the one we do now that we have better computers, but you do still see this sometimes. So we're going to test for how certain we are of our tree by going back, resampling our data with this bootstrapping technique, making a new tree, and seeing if it's the same or different. And then we'll just do that again and again and again a bunch of times. So in practice, what we do is we resampled our data a whole bunch of times. We've made a whole bunch of different trees. The tree that has the highest criteria score is shown, right, by our parsimony, our model-based approach. And then what we do is we show what are called bootstrapping values for each node. So, for example, here, we've got 5 taxa in this tree, and what this is representing here is that I did 100 bootstraps. So I took my tree, I resampled my data, I made 100 trees, and 98 out of 100 trees, I had A as the outgroup to everything else. So when I look at my phylogeny, well, I'm actually really very certain of that part of the tree, right? Because 98% of the time, A is the outgroup to everybody else. This part here is a little less certain, right? So E being the outgroup to those, that only happened 91% of the time. But then like 98% of the time, we have these 3 together, something like this. And if you think about this node here, this 67, for B and C being more closely related to each other than to D, well, 98% of the time, B, C, and D are more closely related to each other than they are to A or E. 67% of the time, it's B and C. That means that about a third of the time, we got a tree like this, or we got a tree like this, right? Where B, C, and D are still closest relatives, but 31 out of those 98 times, you didn't get B and C most closely related. You either got C and D or B and D. So when we're looking at this phylogeny, okay, we're very certain and sure of this part of it. We're very certain and sure of this part of it. This part in here we're less certain of, right? There's a 2/3 chance that B and C are closest relatives. 1/3 of the chance it could be something else. But we're very sure that B, C, and D are all more closely related to each other than they are to A or E. So we don't ever think that we have the correct tree that's perfect, but we represent a tree, and then we have these bootstrap numbers to indicate how certain we are of particular parts of the tree.